This presentation is prepared for those students enrolled in EPO 322, Diesel Engineering 2 simulation being held at the California Maritime Academy. This is presentation 13, which is diesel engine start air systems. One thing I want to point out is there is a good website. It's a Maritime Academy in England that has some very good information and graphics specifically on the start air systems, and it's worthwhile going to that site and looking at some of the information they're giving. When we're talking about starting a diesel engine, ambient air temperature is a very important factor. You'll find this when you're talking small diesels and you're trying to start those up. What I'm thinking of is your lifeboat diesels, and you're trying to start those up, say, at Alaska or up in Portland during the wintertime. Diesels are compression ignition engines. So if the air temperature in the combustion chamber is low, it may not be enough heat, high enough temperature to get it to explode, to get it to start to burn. This also includes the temperature of the engine at cold temperatures will also affect that. The other part of that is your lube oil temperature. If your lube oil temperature is quite low, then what will happen is you'll have more resistance because of the higher viscosity. If the oil is cold, it's going to be a higher viscosity, more resistance to be able to turn the engine over, and then that means a slower turning speed on the engine, and then that will affect the ability for the engine to start. Compression. If your engine has low compression pressures, again, your temperatures and pressures in the cylinder may not be high enough to ignite the incoming fuel air charge. Direct injection air start, which is very common on all your larger engines. As you're injecting air into the cylinder, it's expanding, and that can have a cooling effect on the cylinders, which will also affect this. The reality of the matter is this is why most diesel engines in a standby condition are kept hot. Typically, what's going to happen, you're going to keep the jacket water hot and you're going to keep the lube oil hot. Typically, you'll have in the jacket water system some type of heat exchanger to make sure the engine's always up to temperature. It could be heated from the main engine. It could be heated by an electric or some other method. But normally you keep these engines hot. So starting methods on small auxiliary engines, you can use an electric motor, just like your car, to start it. Hydraulic motors, we have an example of that on the Bear, on the emergency diesel generator. Air motors, you've heard this on large diesel trucks. You can hear the air motor turn to start them up. Some engines, the smaller ones, in our case, we have the Lister lifeboat engines, we're hand crank. Hand crank is usually an auxiliary method. There's not many around that do that anymore, but it is nice in case you have the last chance and you need to get the engine to start. By the way, with hand crank though, diesel engines have too high a compression for you to pull them through. So what you do is you have a compression release, and what happens is there's a lever on top of the engine, when it's on top of the valve cover. When you flip that up on the listers, that lifts one of the intake valves, and then you start to crank the engine, and what you're doing is you're storing energy in the flywheel, and they have a large flywheel that you're storing that energy in, and you're cranking it, getting up to speed, and then you drop the compression release very suddenly, and that should give you enough momentum that you can pull it through compression and get the engine to start. All right, so again, in large and small industrial diesel engines, you're usually preheating your jacket water and lube oil. In some cases with small auxiliary diesels, you may have a glow plug, and we'll show that in a minute. Compression release I just mentioned on the hand crank engines. And you can short side use starting fluid. Starting fluid is typically ether. It can be purchased at any automotive store. It's commonly used by farmers to start their diesel tractors out in the field. It works quite well. What ether does is you take your air cleaner off and you spray a small amount of starting fluid into the engine. Crank it over when the engine starts. Then it's just that initial, just to get at the initial burn. Then you'll get enough heat that the engine will continue to run. But ether is very combustible. That's why you're squirting it in. It will ignite at a lower temperature and in the cylinder. The problem with that is they've had on ships in an emergency with people in the lifeboat that someone sprays too much ether into the engine, and then it's literally will blow the head off the engine, and you don't have that diesel for in then an emergency situation. So the Coast Guard looks for starting fluid on a ship, and if they find ether, it is illegal to have on board. So if you find it on board, you should get rid of it. Glow plugs. In this case, the glow plug on here is right up here into a pre-combustion chamber. This is an old diesel, but what happens is you've got a pre-combustion chamber here. To start up, that glow plug would heat up the air in the pre-combustion chamber, and then you would, when the engine is turned over, you would get the spray of fuel into that heated air, and that would ignite and then blow into the main cylinder. Glow plugs are not used very often on marine engines. I really haven't seen them, but it is an auxiliary starting method. Who I do know still uses those today is like Mercedes diesels, but the glow plug now is in the main combustion chamber. I don't believe that it's in the, they still use a pre-combustion chamber. Electric starting. Electric starting is popular with small engines. One of the things I want to make you realize, though, is the amount of current involved. When you're talking of electric starting, you're even talking of a big block V8, you're talking hundreds of amps on start. Look at the cable that is going from the battery to the starter. It's very large. That's because there's a lot of current. Now you're only cranking for maybe 30 seconds or 60 seconds. In fact, if you crank on your starter on your car, if you turn that over for too long a period, you will melt the starter down. They are not designed to run for more than about 15 to 30 seconds. That's about it. And if you crank your engine over and it's not starting, then you need to wait for 4 or 5 minutes. After, crank it for 15 seconds, then wait 4 or 5 minutes and crank it again. Don't just keep cranking because you will melt the starter motor down. I've seen that happen. Now, in this system, just like your car, you typically have a solenoid. What the solenoid does is you have a small amount of current that is going to a button. In this case, on, let's say, it's either a starter button or on like your car, it's the keyed. And that small amount of current, that when you press the button, that current goes into the solenoid and pulls an armature down to close the main contacts. The main contacts are going to hold that heavy current, which is like 200 to 400 amps, going to the cranking motor. Sometimes on your car, by the way, what happens is when you try to start it and you hear a buzzing noise, what's going on is your battery voltage is low, and the solenoid uses a magnetic field. And if the voltage is low, it doesn't have enough oomph to pull the solenoid in, and the solenoid will come in, drop out, come in, drop out really rapidly and cause that buzzing. And that's an indication that the battery is drained and does not have enough voltage. So again, the solenoid is using a small voltage, or excuse me, it's not voltage related so much as current related. It is using a small current to activate a solenoid which pulls in main contacts that handle the heavy current. So if you didn't do this, if you would have put a push button in the main start system, that heavy current through that button would burn up the switch fairly quickly, and can you imagine on your car, if look at the cable on your battery, if you had to run that up under the steering column, how much of a disadvantage that would be. So literally you're using about less than an amp on your starter, the starting switch, to handle 200 to 400 amps going to the motor. Very common on larger, say on forklifts, in some cases emergency diesel generator, where they use this electric, you'll have 24-volt system. The 24-volt system gives you a higher cranking speed, more power. That's important for a diesel. You need to spin the diesel over fairly quickly to get that compression ignition, to get the temperature up. And normally the way you'll do that is to get the 24 volts. In most cases, you're taking 12-volt batteries and connecting them in series and in parallel. You connect two in parallel in series to get the 24 volts, and then they may even have them in series to get in parallel to give you more amperage. So again, what you'll do is if you want to go from 12 to 24 volts, you put two 12-volt batteries in series, and to get more cranking amps, then you would put them in parallel. Now, a Bendix starter is very common for the electric, especially like in automotive. When you look at this, the Bendix itself is what is going to engage the drive gear. You don't want your starter engaged all the time, because it is turning at quite a high speed and it's engaging with the flywheel. And it's basically, if the engine starts, once you start revving the engine up, you would over rev the starter motor, and the windings would come out of the motor. Most of these starter motors are DC. Most of them today are still a series type DC motor. But you have a drive gear. Let's see if I can get. You have a drive gear on the end, and that has to be pushed forward to engage the flywheel. The Bendix itself typically uses inertia, and there's a scroll, if you want to put it that way, on the shaft, so that as it starts to turn, the drive gear will move towards the flywheel. Another one, in some cases, you actually have a solenoid that actually has like a fork that pushes the gear into mesh. So anyway, on this one you can see where you can see that what you're trying to do is the drive pinion has to be enmeshed into the flywheel for when you're trying to start, and then disengage. Again, this is typical with electric. The problem with electric, there's a couple things. One, it's typically not a real high cranking speed. And number two, if you drain the start air batteries for an emergency diesel generator, and you don't have any electric power on the ship, how are you going to charge the batteries back up and so that you're going to start the emergency? Where I have seen electric on merchant vessels for the emergency diesel generator, I have seen also an air start motor, so it literally has both, And then what they'll do is have a small tank and a small air compressor. And the air compressor would be a hand start little diesel a diesel compressor, and that then you could switch from electric to pneumatic and start up this little hand crank compressor, fill your start air receiver, and then start the motor that way. But that is the problem with electric is if you drain the batteries, then how are you going to start it if you're trying to start the emergency diesel generator and you're dead ship and don't have power? A much more, I think, a better system is the hydraulic. Hydraulic is very, very good because it gives you a high amount of torque and a high starting speed. They're expensive, but it's for a small diesel, it's a very, very good system. Now, to store the hydraulic fluid, you have an accumulator. Be very, very respectful of a fully charged accumulator. They're typically 2,000 to, I've seen up to 4,000 pounds. When you get into high pressures like that, you better respect the amount of energy that is being stored. And with all of these systems in reality, you need to think about that. It takes a lot of energy to start a diesel engine. And you're storing that energy. Before we were storing it in a battery, and this we're storing it in a hydraulic accumulator. Specifically, if you are working with one of these systems and you accidentally release a component that's under that kind of pressure, it will come out at an extremely high velocity and speed, and typically someone gets hurt. So you do need to respect these systems. But over on the right hand side, you can see that you have an accumulator that's going to be pumped up with high pressure fluid. Then what happens is when you go to start, a solenoid is opened and that fluid goes into a hydraulic starter motor. Now they still have the Bendix, they still have the same idea that you have to have a gear that's going to come out and mesh with your flywheel. It's just instead of electricity, an electric motor turning it, now you're moving to hydraulics. And on this case, they're showing you a starting lever. When you lift that starting lever, that would allow flow of fluid into the motor. As the motor starts to turn, the Bendix would be thrown out, engage the flywheel, turn the engine, and then that fluid coming out of the motor then gets stored in the reservoir. Once the engine starts, then you would shut off fluid going to the starter motor, and you would have to go to the hand pump and pump the fluid out of the reservoir and back into your accumulator. Most ships for the emergency diesel have an engine-driven hydraulic pump that will pump the accumulator full so that you're not going to have to do that by hand. The hand part, though, that is your backup, so that if accidentally that you discharge this hydraulics and need to start the engine again and it's been discharged, you can pump it back up by hand. One of the things that normally happens with this, by the way, is when you shut down a emergency diesel generator, do not shut it down by tripping the flapper valve on the intake of the engine. Like on the Bear, if you look at our emergency diesel generator, there is a trip that you can trip to shut down the emergency diesel generator that shuts off the air. Some people I've seen in the past, and I've had a problem with this, I've needed the emergency diesel generator and it didn't start because someone had shut it down improperly. I've had this happen to me twice. If you trip the air with the engine running, you're shutting off engine air to the engine, but it's still running and it still has the mechanical fuel injection. You're going to be injecting oil into the cylinder until it stops. That diesel oil will now get into your sump and contaminate the lube oil. And then what ends up happening, and that's a bad idea by itself, is the people will forget to reset the trip, walk out, and then when the automation tries to start the diesel generator up, it can't. It'll drain all your hydraulics spinning the engine, right? And it can't start because it doesn't have air. And then when you come up there, you got to reset the air start, the air trip, but you also have to pump up the hydraulics, which takes time. Again, you're familiar with the one on the Bear, so you should have a good idea of how these work. Let's go ahead and talk about direct injection air starting. Large engines typically are air start. Again, respect the air start bottles. They are a bomb sitting there. The whole idea of having a pneumatic starting system is you are storing huge amounts of energy in those bottles. The size of the bottles is very dependent on the size of the engine. And what's going on is you're injecting air into the cylinder, so instead of at the proper time to turn it in the proper direction. Again, one of the things you think about this, instead of burning fuel to have that force being pushed onto the piston, you are injecting air into the cylinder direct. Now, if you're talking a large slow-speed engine, I've seen the tanks as large as, say, about 15 foot in diameter and 15, 20 foot long. They can be very, very large tanks. Now, this drawing, what we're talking about, if you look, you see the air receiver, and then you see a main start valve and a slow turning valve. The slow turning valve is typically only would be found on a propulsion diesel. It's not that common, but when you're before getting underway, most ships will roll the engine over on air prior to starting it. When you roll it over on air, if it's direct drive, which a lot of propulsion engines are direct drive, then you're turning the prop. If you're turning the prop, then you're pushing the ship alongside the dock. Now, this can be a big thing. If you spin the engine over at too high a rate of speed while you're at the dock, there have been cases where it's broken the mooring lines, pulled down cranes, or broken the checks with loading of crude. So anyway, the slow turning valve is all it is. It's a smaller valve so that the engine would turn over slowly, not enough to start. It's more to just roll the engine over ahead and astern prior to starting. After that, this air is going to your distributor. On a mechanical system, the start air distributor is run off the camshaft. And again, it has to be timed to the engine, with just like where you would inject fuel into the cylinder at the proper time to turn the engine over. In this, we're going to inject air into the cylinder at the proper time. Now, after that, you're seeing a non-return valve. That is a requirement. When you're rolling the engine over, what you don't want, as with the start air valves are open, you don't want combustion gases going back through the air start system and into the air receiver. So it is a requirement to have a mechanical non-return valve in the line. Also, if you follow it down, you see you have flame traps. The flame traps are there to prevent an explosion in the start air system. What can happen on you is that, and I think you've probably seen this on the Bear, that when you drain the start air receivers, you will get some lube oil from the compressors. Well, what happens is if you have oil that is in the start air system lines, that can burn and cause an overpressurization. You notice the safety valve in this drawing. On the Bear, we actually have burst discs. In other words, that if there was a combustion to take place and that overpressurization, the bursting disc would open up, would blow out, and dissipate that into the energy into the engine room instead of damaging the system. And then you would have to replace the bursting disc afterwards. So, and then what you're seeing is the start air valves themselves. And the start air valves have two lines. One is the air coming into the valve, and the other is the pilot that activates the valve. So what you want to think about this is you've got the main start air coming in. It's going to all the valves. The pilot is coming off your air start distributor, and that's the signal that tells it to open to inject air in at the proper time. So again, the starting air explosions can happen on engines, and you will have typically a non-return valve in the start air system, a bursting disc, a flame arrestor at each cylinder, and these are to help prevent with that type of accident. So on the left, and this is very common, I've sailed with those a lot, both of these. These are big slow speeds, one for Wärtsilä and one for MAN. And you see what you have is a block of a heavy block of steel, or in one case brass, and then you see the holes through it. The idea is kind of like the fine mesh screen with a flame arrestor. As the flame goes through that, that will quench the heat out and quench the flame. On the Burmeister Wain, this is their bursting disc. This is again a large slow-speed engine. They do have a bursting disc so that if you do have a start air explosion, you would not damage the equipment. By the way, the Enterprise engines, our main engines on the Bear, also have this. This is the drawing from MAK. It's similar to what we were talking about before. Hopefully you've, and if you haven't, you need to go down and look at the MAK to find all these components. You know where the start air bottles are. Typically, we use an electronic activation to put air to the unit, but you also have a manual start air valve that can, and so you can either, again, that valve can either be triggered automatically from the automation, or there's a lever that you can pull on to start it. You also know there's a fuel rack limiter. When you start a diesel engine, the governor is going to go to wide open. It's going to want to open the fuel rack to its maximum. That's because it's looking at 900 RPM and you're doing 0. It's going to try to give it the fuel. The problem with that, once you start rolling it over, if it was to start with full rack, the engine, because you're not producing electricity, there's no load, and the engine would seriously overspeed. Before the governor could react and shut the fuel back down, the engine could overspeed enough to actually damage it. So what happens during the start cycle, the fuel rack is limited to a much lower setting to prevent overspeed. Now on the MAK, this is the start air shutoff valve. In yellow, that's the little pilot that's going to be moving up and down, and that is activated by the solenoid. Typically, again, on this, we've talked about this a little bit earlier on other systems, but to get the force to move that valve, you have an electronic solenoid that's moving a little pilot valve that is controlling air, and it's actually air pressure that is going to move the main pilot and the main valve disc up and down to allow air to go through it. So this would, when you get a signal, you push the button on the console on the Bear to start the diesel generator. This solenoid is activated, that valve opens and allows air to go to the start air system to initiate the cycle. And that's what it looks like in real life. This is on the flywheel side of our MAK diesel generators. I like using these as an example because it's readily available to you. On the start air valves, it is a good idea to check these on a regular basis. What can happen is start air valves can burn and start to leak. And if they leak, then when the engine's running, those combustion gases can get into the start air line. Typically, depending upon the engine, if it has large lines coming in, for the start air lines are external, what happens when the engine's running, you'll put your hand on each of the air lines and walk down the engine and check to see if they're hot. If they're hot, that means that you have a start air valve leaking, and at the earliest convenience, when you want to shut that engine down and pull the start air valve in and put a new one back in. On Burmeister Wain, and I'll actually talk about this more later on in this PowerPoint presentation, they actually have you do it with when you import and the engine shut down. You on the big slow speeds, you're going to open up all the indicator cocks. There is a valve that can be shut so that the air doesn't go to the distributor, which would prevent the main engine from rolling over, but would allow you to put air on the system and put air to every one of the start air valves. So with them, you put air onto the start air system, and then you walk by each indicator cock and see if there's air leaking out of the indicator cock to check them. But anyway, any engine that you have that has a start air system, you should be checking the start air valve for leakages on a regular basis. Now, the other thing on the distributor, it has a camshaft lobe on it. And again, this is the one that is giving you the pilot signal to go to the start air valve for it to open and close. One of the things on these, those little cams and followers, they can wear over time. Most of the systems are set up so that when the engine is running normally, the followers are sucked away from the camshaft lobe and don't touch it. But then when you go to start the engine, air pressure is applied that snaps them against the camshaft lobe. But again, you have this camshaft lobe that is going to trigger one cylinder at a time for air delivery, and it's going to do it in the proper sequence. So this is for the MAK. In green is the little follower. The air would come in. The air would come in here, act on top of this surface, push this up against the camshaft lobe, and then as this is activated back and forth, the air coming in here would be able to go this way and go out to your start air valve, and that would be to activate it. The start air distributor, this is again the drawing from MAK. This is where it is on the bear. Right here. This is your flywheel. There's your start air distributor. If you haven't seen it, go on the bear and go look. And the camshaft itself is behind this, and the camshaft lobe to drive the start air distributor is right off the end of the camshaft. Now, the start air valve is located, as this says, in the cylinder head, and this is your pilot air from the distributor, and that air acting on top of a piston will push the valve open, allowing air from the start air line to enter the cylinder. So this is the MAK, and this is your pilot control air up here, and then this is your main start air coming in. So when there's a pilot air comes in from the air distributor, start air distributor, then the force acting on this compresses the spring. This opens and allows start air into the cylinder. Whoops. This is your, right here is for the start air system. This is your, when you start one of these engines, watch how it works, but that will limit your rack on startup so you don't overspeed. So your starting fuel limit cylinder. On the Burmeister Wain, this is the start air valve coming off the side. Right, there's your pilot signal. This is the start air coming in. And again, on these, one of the things you can do is just put your hand on the line, and if you have leakage, the line will be hotter than the others. On this side here, by the way, there's your bursting disc on this particular unit. And this is the MAN Burmeister air start valve. This purple color, pinkish color, that's the piston. You put air on top of this, and then this opens. And then there's their start air distributor. And this is just giving you the air signals to it. Alright, this is off the Burmeister Wain and their main stop and slow turning. One of the things on the safety factor, when this engine is shut down, not only will you be stopping air to the cylinder here, but there are other root valves that are closed. Remember that with any diesel engine, when the engine's shut down, you want to secure the air for safety. If you were going to work on it, if you were going to go into the interior of the engine and work, you got to make sure that your start air is secured. In the case of the main engine, you don't want to get an accidental start while you're up against the dock, so you're going to make sure that you're going to block air to the engine to prevent an accidental start, and these act as a block valve. There's your turning gear on a big slow speed. Valve 115 that they're showing there, that's an interlock. If you engage the pinion with the flywheel and accidentally go to start the main engine and roll the engine in over, the turning gear motor would be destroyed with an overspeed. So what they do is they put in an interlock that will prevent you from rolling the main engine over if the pinion is engaged with the flywheel. Again, this is their start air showing some of the different connections. Now, one of the interesting things about the Kongsberg system, there's a lot of information there available to you. It's too bad we don't have more time to go through all of this in a lot more detail. But I want you to put your attention to the maneuvering system. The maneuvering system on the Kongsberg system has all the actual pneumatic control valves with their symbology to operate this engine. So particularly on this is their depiction of the cylinder heads, your start air valves. This is your start air distributor. These are actually for the reversing mechanism for your fuel pumps. Here's your slow turning, your main starting air valve. But these are all the pneumatic control valves. In case, by the way, this one is sending on when you're rolling over the main engine to getting it ready to start. This is the signal that goes up to the puncture valve on your fuel oil distributor. We're going to talk about this a little bit later. But one of the things I want when you're looking at this, look through this system and try to get as much information as you can. There's a lot of information there for you. Also on the control system, this is for NOR control. I have sailed with many ships that this is in a brass plaque with little LEDs, and that's mounted right at the control station. And this is giving you kind of, if you want to put that, a flow diagram of what's happening. On the left-hand side, it is telling you whether you're under bridge control or engine room control. It's indicating whether that is giving you a stop signal. Have you been, is a head or a stern been selected? Start block is if there's different reasons that will cause this. Many of them over here, the main engine shutdown can be part of this, and there's some other things that will do that. But is the start of the main engine being blocked for a reason to do with the automation? Above reversing level, we'll talk about this when we get into the reversing, but if you are on a direct drive engine and you are moving through the water at too high a speed, you've got that propeller in the back that is revolving the main engine. To try to reverse it, what happens is you have to admit air to first slow the prop down, stop it, and then reverse it and start it spinning in the opposite direction. I want you thinking about that you're going to use a lot more control air when you have speed to reverse an engine that is making its way through the water. It's much more air. And if you're usually doing above 6 or 8 knots, you'll run out of air before you can start the engine. Well, this above reversing level, what that's telling you is the vessel has too much way, right, and the propeller speed's too high, so it's not going to even try to reverse the engine until the propeller speed slows down. And that indication there is that the automation is waiting for the prop to slow down before initiating a start. All right, so a head and a stern cam position. This is basically on a Burmeister Wain. These are actually for your fuel delivery. And then again on this, if initiation of a start is initiated, if the puncture valves, the fuel off, that is the puncture valves, are they activated? If the engine doesn't start after 6 seconds, the automation will stop this and try and start again, and you'll get a repeat start. If it doesn't start the second time, then it will do this repeat start number 2, which is your third attempt. If that fails, then the automation will send an alarm to the bridge and to the engine room that there's been a main engine start failure. All right, this is for our Enterprise engines, and it is the same diagram that we've kind of talked with before, but gives you the system for that. Now, one of the things too on the start air system that I put in here, this is your start air valve on the old Sulzer. This is an old Sulzer loop scavenged engine. But notice how the start air valve is not directly in the head, it's up a ways, and notice how this area decreases before it goes into the cylinder. The poppet valves on start air valves have been known to break, and literally the poppet will drop off and then enter the combustion cylinder where the piston strikes it and pushes it up into the cover. Well, that's why they've done this, by the way, when you see these, is that so if this breaks, then the poppet cannot drop into the main cylinder. So anyway, on these, again, this very similar to what we've been talking about. On the older systems, there's a start air distributor and there's start air valve. This particular one had an air signal to open and an air signal to close. Here's their start air shutoff valve, and again, these are used as a block valve, and they can be triggered either manually or automatically through your throttle control. And then this is their control system for the start of the engine. And these are the pneumatics. Now, in the newest engines, the electronically controlled, a lot of these pneumatic controls are going away and we're going to electronic computer controlled. And on the newest engines, everything is controlled off the computer. They have a pneumatic logic unit on these engines. Both Burmeister Wain, the MC engine, and the Sulzer RTA engines are pneumatically controlled unless you get into the electronics. That's the end of this presentation. I hope that it has been informative. Thank you.